And welcome to TI's new product update webinar series. Today we have automotive product marketing engineer George Lackas ready to talk to you about improved traction inverter system efficiency at a lower cost with real-time variable gate drive strength. But before we get started, just a few quick notes. On the left-hand side of the page, you will find a Q&A box where you can type in your questions throughout the presentation and we will answer them in real time. You can also view additional resources related to today's topic located on the right-hand side of the page, such as product folders and evaluation modules. We hope you enjoyed today's session, and I will now pass it over to George to get started.
Good morning, everybody. This is George Lackas. I'm the automotive isolated gate driver product marketing engineer at Texas Instruments, specifically responsible for traction inverters. Thank you for joining us. So today we're going to talk about how we can enable higher efficiency in your traction inverter designs while reducing system costs. So looking at the agenda, we're going to look at, first of all, the key traction inverter design considerations, what isolated gate drivers we have at Texas Instruments to address and improve those trends. And then we're going to do a mini deep dive on our new isolated gate driver, which is ISO 262 compliant, that employs real-time variable gate drive. We're going to talk about the traction inverter operating conditions that impact the power switch, essentially the power module that carries the current and delivers the current to the motor. We're going to look at the concept of real-time variable gate drive and how we design for it. And we're going to show some measurement data we've taken to show the impact of the real-time variable gate drive strength on traction inverter efficiency, as well as power stage trends and overshoot. And last but not least, we're going to share some design support tools with you. So what is a traction inverter? Essentially, a traction inverter is a subsystem in the electric vehicle powertrain that takes the high voltage from the battery and converts it to an AC voltage. That's the term inverter, and essentially powers the motor. It controls the motor speed and torque, and it directly impacts efficiency and reliability. And we see that are becoming design challenges for the traction inverter design. What you will see on the right is, one of the traction inverter designs on the EV platform. EVs today have at least one traction inverter. Some models actually have more than one. So one on the front axle, one on the rear axle, and even some higher end models actually have a traction inverter per wheel. So efficiency and reliability are very important. So market trends in terms of inverter and motor control. In terms of the technology trends, we're seeing increased power levels. Today's mainstream vehicles are roughly in the 60 to 70, perhaps 80 kilowatt power level range. But we're seeing for next generation electric vehicles, power levels increasing anywhere from 100 kilowatts all the way up to 500 kilowatts or even more. We also see the trend to use higher battery voltage, so switching from 400 volts to 800 volts. The reason for that is because there's now a lot of silicon carbide FETs that can help with the efficiency, and those operate at higher voltages, 800 volts or more. And so we now have the opportunity using these new power stages to increase efficiency and improve the traction inverter design. Higher power density is another trend. We're seeing targets up to 50 kilowatts per liter. And on top of that, higher system integration in the traction inverter. And last but not least, of course, maintaining safety and reliability for the passengers. And so here we're talking about functional safety up to ASIL D. What you see here on the block diagram is essentially a traction inverter application showing the main blocks, and here's where our gate drivers come into play: high side and low side driver powering a half bridge. For a 3-phase motor, you would have 3 of these. For a 6-phase motor, obviously 6 of these, and therefore 12 gate drivers. So what are the key traction inverter design considerations? So if we go from left to right, so in terms of electric vehicles, are some high-level design considerations, and of course these are kind of common sense. How do we maximize the range for the same battery charge? How do we improve the EV infrastructure and improve EV charging as well, what we call fast chargers? How do we make EVs more affordable? If you look at the EVs today compared to internal combustion engine vehicles, they're still about roughly $12,000 more. And last but not least, again, how do we enable safe operation for the passengers? So then as we transition from the EV to the design considerations for the EV, of course, it's efficiency to maximize EV range, cost to lower the cost of the vehicle, size to make sure that the weight and the size of the vehicle do not unnecessarily increase, and protection and reliability. What set of protection and monitoring features the inverter should have to ensure safety and reliability. So then looking at the inverter subsystems, what are the critical subsystems that we need to design for? So you have the microcontroller and controller that work hand in hand with the gate drivers. We have the bi-supply, and we have those as well, and they're highly integrated. The feedback loop to make sure everything is done real time and as accurately and precisely as possible. The bus bars, those also affect efficiency. The gate driver itself, of course, and last but not least, the power modules, whether silicon carbide or IGBT, because these are the modules that will be dissipating current and therefore are under a thermal stress. So as we see these trends and we design for them, we also see the need to integrate more circuitry and more features into the gate driver itself. So modern gate drivers today integrate, they don't just turn on or off the FET. They do a lot more. So they integrate features such as isolated ADC sensing. So we have, for example, 10-bit analog to digital converters inside the gate driver, anywhere from 2 to 6, depending on the product, that you can use to sense anything you want, but most importantly, the power module temperature and usually the DC bus voltage, but you could use them to sense the phase current or even the internal voltages on the gate driver itself. On top of that, we offer a host of protection features such as DSAT and overcurrent protection. We also monitor our own bi-supply voltages, both for under voltage and over voltage events. We monitor the FET gate for reliability. We can program into the gate driver we have a variety of multiple thresholds to program into the gate driver to achieve and ensure safe state. And also today's gate drivers have their own built-in self-tests where they will actually check all the voltages, all the comparators inside the gate driver as we power on to make sure everything is up and running to not only turn on and turn off the FET, but also be able to protect and monitor. On top of that, what we're talking about today is we have added a feature we call real-time variable gate drive strength. And this is a product that I will introduce today as part of the solution to these design challenges, which is called UCC 5880-Q1. You will find it on the web. We're in pre-release phase today, and we will be releasing to full production by the end of the year. So this product essentially combines all the features that I talked about. It's a very strong driver at 20 amps, full drive strength. And so it helps with essentially eliminating any buffers you might have in your design now to lower the cost in the area. It offers real-time variable gate drive strength to optimize between efficiency and transient overshoot. We offer very fast short circuit protection in the tune of 75 nanoseconds to make sure we protect the silicon carbide as fast as possible during a short circuit event. Very high noise immune, over 100 volts per nanosecond. As I mentioned, it's fully ISO 262 compliant, and that helps you achieve up to ASIL-D level functional safety. It comes with a 4 megahertz SPI bidirectional bus, so you can program into it and monitor out of it any parameter that you want, over current, over voltage, under voltage, over temperature. And so it's quite flexible. And also we include a quite, we feel, differentiated feature, which we called gate threshold voltage measurement at every key on. Essentially, you'll be able to see and predict if the power switch, the silicon carbide FET, is beginning to fail. And so that's also included in the driver. So today's drivers are vastly different from yesterday's drivers. So what are the major challenges that we're trying to solve here? If you're a traction inverter designer, you have to worry about many things. You have to worry about the motor current, the loading, the temperature, and the battery charge and voltage, because all these affect electric vehicle efficiency, EMI, as well as the overshoot on the silicon carbide FET. And they can impact the battery size, cost, drive range per charge, and reliability. So the design challenge is how to then implement a gate drive, a real-time variable gate drive, where you can switch at will based on the different operating conditions between a weaker gate drive strength and a stronger gate drive strength. Because when you do that, then you can optimize these key design parameters, efficiency, EMI, and overshoot, literally on the fly. And what I'm showing here on the right is kind of some examples, right? Because, for example, in terms of load current, and we use, by the way, these are real drive cycles that we used. These are called worldwide harmonized light vehicle test procedures, where you can see essentially, how drivers drive electric vehicles, right? So the majority of drivers obviously drive at a normal speed, but there are drivers that do speed, and at the same time, there's drivers that accelerate or decelerate fast. And then when you look at temperature, obviously, conceivably, you could start a vehicle at very cold temperatures. And cold temperature does affect the safe operating area of the switch. It actually lowers the working voltage. And in this particular case, you see a decrease of 50 volts on the working voltage of the switch. And last but not least, the battery itself makes a difference. What I'm showing here is just a single lithium-ion cell, basically 4 volts. So for an 800-volt design, you would multiply obviously by 200. But when the battery is full, that also tends to stress the silicon carbide FET switch as well, in terms of overshoot. So all these operating conditions and the fact that they change as the driver drives the vehicle, from starting the vehicle to parking it, affect the operation of the traction inverter. So real-time variable gate drive strength will enable increased efficiency, overshoot control, increased power density, and reduce system cost by essentially enabling you to tune the inverter design real-time to address these challenges. So what is variable gate drive strength? So on the left, I'm showing a traditional gate driver output structure where it's basically a single driver power stage. You see the internal FETs Q1 and Q2, and really you determine the drive strength by the internal RDS(on) of those FETs, as well as by the internal gate resistance of the power switch, and by the external resistors that you see here, R on and R off. But you cannot really vary these, any of these. You cannot vary the strength at all. So there's two ways to then implement variable gate drive strength. In other words, varying the gate drive strength on every PWM cycle. So one is, of course, discrete. You reuse the single power stage, and then you add a bunch of components. What you see here is basically two FETs that are responsible for the enabling and disabling the drive strength adjustment, and the external resistors, and then a digital isolator that you also need to enable the FETs themselves. So this circuit in million unit quantities roughly is less than $1, but it's still significant, right? Why not save $1? And it also takes up some area, but it does work. But now the smarter way, of course, to do it is to try to integrate this implementation into the gate driver, and we've done that. So what you see on the bottom here on the right, you see our new driver where we integrate essentially a dual split output power stage. So now we essentially integrate 4 FETs, because not only do we give you adjustment control, we also give you separate turn on and turn off control of the power switch per output. And so what that does, obviously, it completely eliminated the discrete circuit, reduced cost and complexity, and it's much easier to control. In this particular product, we actually offer you 2 ways to control the drive strength. One is through the 4 megahertz SPI bidirectional bus. The control will be coming from the MCU. But also, we give you the ability to set the drive strength at power on without the SPI bus by using 3 digital input pins that we have. It's essentially a lookup table that would be loaded from the MCU also. And you'll immediately be at the drive setting of your choice at power on without having to use the SPI bus. So how does that relate to the power switch itself? So what matters a lot is the fact that the gate drive strength affects the switching speed of the power switch, as well as the voltage in terms of over voltage. So so essentially you have to size the gate resistors accordingly to select weak or strong gate drive. And you do that to be able to, again, optimize efficiency versus drain to source overshoot on the silicon carbide switch. So what you see here on the left is we've actually had some test conditions here. We're using the Wolfspeed XM3 power module. It's a silicon carbide module, 800 volt bus, 450 amps of load current, and right now we're just using 25 degrees of ambient temperature. And so what you see then going from left to right is if you want weak drive strength, if you want strong drive strength, you obviously use lower value external resistors, 1 ohm in this case. And what you see here is, again, in engineering, everything is a trade-off, right? So what you see here is the slew rate, because it's essentially a slew rate control driver. So the slew rate is fast, so the slope is much sharper to the expense of a higher transient overshoot. And so if you switch to the weak gate drive, depending on the operating conditions, and you will see here in the rectangle, now we're using, of course, higher value resistors, 5 ohms externally, then now you see that the slew rate is slower, so less sharp, but now the overshoot is much smaller. And the overshoot is basically the result of strain inductance PCB that causes overshoot. It's no matter how much you optimize your PCB design, you will always get some. But this is how essentially you would affect the power switch transient and slew rate when you use weak, strong, or weak gate drive strength, and the results speak for themselves. When we use weak drive, you can see, and I'm just going to go straight down to the VDS results. You see that we have about 1,000 volts, measuring about 1,000 volts, 40 millijoules of turn-on energy loss, and almost another 40 millijoules of turn-off energy loss. But then when we use strong drive, we get a different set of results. You will see that the energy loss is basically 2x or more than 2x less, over 2x in this particular case, the turn-on, and about 2x less on the turn-off energy, but the overshoot is almost 150, 160 volts higher, and that's a trade-off you will be playing with. The good news is that with this driver, you can do both. Let's look at a battery cycle, because that maybe should give a little bit of understanding of how battery voltage plays a difference. Because when a battery is fully charged, basically from 100% to roughly 80%, you will see then that there's less headroom for the silicon carbide overshoot. And what that means is now you have to employ the weak gate drive that I showed previously, the 5 ohm external resistors, for example, to be able to, as the battery is still in this, in this portion of the battery charge cycle, to make sure that the silicon carbide FET is not getting stressed. You're not going over the overshoot threshold, maximum threshold of the power switch. But as the battery is beginning to discharge, And that's roughly from 80% to 20%, and that's pretty much 3/4 of the battery charge cycle. Then you can begin to employ strong drive strength because you have more headroom for the silicon carbide overshoot window. And so now you have the ability to increase efficiency using the strong gate drive. And that's kind of in a way how you would be going from weak to strong gate drive throughout the battery charge cycle. Now, designing for real conditions. As I mentioned, as I showed before, we do use and have been using and will be using real drive cycles. And so what you will see here is on this particular graph, the y-axis is the inverter peak current, so the motor current, and then on the x-axis is basically the time. So you will see that in most cases, you know, you will not have to use a weak drive that often. But you have to design your inverter to be able to do that. And in most cases, you should be able to use strong drive to really impact and improve the efficiency. And so what I'm showing here is some kind of design guidelines. You know, so when the load current is high, when your peak battery voltage at maximum charge is over 80%, and when you're starting up the vehicle or operating the vehicle in cold temperatures, depending on where you live, then you should be using weak gate drive. But as the load current decreases from the motor and as the battery itself discharges less than 80% on maximum charge, and when the operating temperature, the ambient temperature has, you know, is warmer or hot, then you should be able to start using strong gate drive to really improve efficiency. And this is kind of what it really sums up to, right? So in this particular slide, the left graph is energy losses versus load current. The right graph is maximum VDS overshoot, maximum VDS voltage over load current. And essentially what real-time variable gate drive strength allows you to do is get the best of both worlds. Basically, as the load current increases up to 300 amps, you know, you should be using essentially strong gate drive strength to be able to reduce the EON EOF losses. You can see here the actual data, how much we're saving. It's roughly 50% energy loss reduction. But then as you're hitting that point here, then you're basically switching over to the weak gate drive strength. So I'm just going to basically drag my mouse here to this graph, and you can see at 300 amps, right, we're basically switching down from the strong gate drive strength that we were employing previously to take advantage of the energy loss reduction. And now you're using the weak gate drive strength to make sure that you are staying below the overshoot limit of the power switch. And so you essentially get to save 50% on the energy losses while maintaining 40% reduction on the overshoot itself. Kind of the best of both worlds, and we'll call this curve or graph the golden curve. So this is some actual data. So this is data we took actually quite recently. And so you can see how essentially, so let me explain the different colors here. The blue here is the actual load current of the motor. The yellow curve is the drain to source voltage on the silicon carbide switch. The red is the gate to source threshold voltage. And then the green is the actual GPIO signal that comes from the MCU to enable our gate driver to switch drive strengths, right? So as we are approaching basically 300 amps, so right here, right about here, you will see that you can see the spike here. You will see the spike is quite high. So we're beginning to essentially approach the silicon carbide overshoot max. So as soon as we hit this current, essentially we are switching down the drive strength from strong to weak. So on the next cycle, what you will see, so we went from 20 amps at 300 amps. So in the next cycle, we're now employing 5 amp weak drive strength at a load current of 350 amps. And you will see then how we reduce the overshoot. We reduced the overshoot by quite a bit, almost 200 volts almost 100 volts. So and you can even see it on the scope shot. The spike was up to here. Now the spike is much lower as well. And you can also see that the current actually increased. So at around 350 amps, we're switching down real time with the MCU command to reduce the gate drive strength and maintain the overshoot, basically clamp it. We're very, very proud of this product. We have a lot of design support tools to help you. You can see it here. We have a really cool reference design. We showcased it first at PCIM 2023, and you're welcome to copy it. But we have training series, technical articles, a lot of design support tools. We have Symmetrics model, all functional safety documents, a power dissipation calculator, and 2 EVMs. One is a 3-phase inverter EVM. You can literally use it to test an inverter up to 300 kilowatts. And we have a single phase. We also have a single phase EVM as well. We are, standing by to assist you with your designs, and thank you very much for joining us. Any questions?
Hey, George, I see a few questions located in the chat box. It looks like one user had asked, when would you want to have a weaker drive strength versus a stronger drive strength?
Mm-hmm. It depends on the operating conditions, but as a high level, you want to use weak drive strength when the battery is full, anywhere from 100% state of charge to 80%. If the load current is high, in this particular example I showed, when you get over 300 amps, you want to switch down to the weaker gate drive strength. And when you're operating the vehicle at basically low temperatures, anywhere from -50 to 0 degrees, you probably want to use weaker drive strength.
Okay, the next question reads, George, besides traction inverters, what other applications can use the UCC 5880Q1?
So great question. Efficiency can be improved with this product in any type of motor. It's not just for electric vehicles, right? So we now see the need to employ this real-time variable gate drive strength even in onboard chargers, believe it or not, because onboard chargers are also increasing in complexity, and especially with what we call one-box designs, where you combine OBC, DC to DC, and traction inverter sometimes. But any subsystem, power conversion subsystem that uses isolated gate drivers can benefit from real-time variable gate drive strength, because at the end of the day, you're improving efficiency. We are seeing we're getting some initial inquiries on, for example, on OBC and DC to DC as well. And also we're seeing inquiries for industrial equipment, or air taxis, what we call eVTOL, or elevators, to give you an idea. So anything that you can improve efficiency, you could use this concept. Now, having said that, UCC 5880-Q1 is a fully AEC-Q100 qualified, functional safety compliant ISO 262 driver. So this product is, full featured. It comes with a certain price point for the feature set. We know we're extremely cost competitive in the market with this type of feature set in a gate driver, but the concept of real variable gate drive can be used, in other subsystems, as I just mentioned. And I think there was another question in terms of the size of the package. So you can go on the web, by the way, if you type UCC 5880-Q1, you'll go to the product folder. On the Texas Instruments website, you can download the preliminary data sheet. It's only 10 pages for the full data sheet. We do require an NDA. So please keep in mind that we have actually a secure folder inside the product folder where we ask you to request access, and then basically we will be asking for an NDA if an NDA is in place. But the package size is basically, it's a 32-pin SSOP, and it's a 7.5 by 10.5 millimeter package with over 8 millimeter of creep-agent clearance. And we're planning to reuse this package for roadmap products because it's working very well for us as well. So.
Okay, and I think we have just one more question that came through the chat, and it reads, is changing from weak to strong drive and vice versa done on the fly, or is there any reliability issue on the system by doing it on the fly?
Great question. So yes, it can be done on the fly, but it's not closed loop control, meaning you would have to essentially on the bench test the driver itself with the gate drive settings you have chosen using external resistors. Once you have set your external resistor value, because really the external resistors is what limits the drive strength, quite honestly. It's the impedance of our own MOSFETs is not as high as what you hang on the outside, the resistors that I mentioned, right? Externally, those set the real drive strength. But it's done on the fly, but you do have to do essentially characterize your design on the bench, set those values, and then you can do it on the fly based on the resistors you've set externally. You can, then have on the fly adjustment between weak and gate drive strength. Great question. I see another question. Do customers prefer using SPI or GPIO? Great question. Great question. It's a mix. So this product is in extremely high demand, and it's a mix. Most customers like the SPI bus because now we give them the flexibility to do a whole lot more than just set the drive strength. They can, as I mentioned, program various thresholds for all the other parameters, protection parameters, under voltage, over voltage, under temperature, over temperature. But we do have a set of customers that they have told us specifically they would not have used this part if they wouldn't give you the option of setting the drive strength at power on through simple digital input pins. So we know those help a lot as well. And those customers basically wanted to do a quick and dirty evaluation of the drive strength without having to learn SPI, especially if you haven't used SPI before. It's quite beneficial to have these GPIO pins to set the drive strength. Great question.
All right, thank you so much, George. I know we are at time now, and I want to thank everyone for joining today's MPU webinar. Next week's MPU, we will have Harrison Overturf here to present on getting started with LMR 36502. Be sure to register for this upcoming session by visiting ti.com/MPU, and you can click on the Register Now link from there. Thanks again, and see you all again next week.
Thank you very much.